Good. So the couple of things that I'm going to talk about in today's class are mostly going to be definition wise. So I'm not going to make you write anything, because the definition that I'm going to cover, I will give you scanned or printed notes, or typed notes in due time. You can also find out this definition in your books, which are very basic definitions. But I would really want you to appreciate and understand the difference of these terms as I go forward. The first thing that is important for us is we need to understand the two terms, distance and displacement. What is and? Okay. So first thing first, displacement কি একটা হবে?
স্যার প্রিন্টেড শীট কবে দিবেন?
I have no idea. I honestly don't, because I don't have it sorted. For these first few chapters, I have a photocopied note that I collected from one of my earlier students, which I believe I can do some Android camera scan, using some scanning app. I can scan it and provide it to you. I hope to do that. আমি definitely তোমাদের কিছু না কিছু notes দিব to help you guide through the discussion as I personally feel preferred. But then again, as long as you don't have the printed notes from myself, from me, you can always go through your basic textbook, which can be Gendo's textbook, or you can also go for the federal book, which is the green one that we talked in one of our earlier classes. If you have any other supplementary books, for example, the AF Abbott or the MNEL, you can also look these up if you have those access to this kind of books. I mean, any logical O-levels book is good for you to find out this part. So the key part that I would like to highlight for distance and displacement is that distance is a scalar quantity, where displacement is a vector quantity. The definition of distance goes by, it is the amount of path covered from when the object travels from one location to another location. Whereas the displacement is defined like this: it is the linear distance from the start point of the object to the end point of the object in the direction from start to end. So we have to say two things. So if I give you a simple example, let's say this is your house. Your house is over here. This is my coaching. You come in a track like this and you reach up over here. So the distance that we'll be covering in reaching to my coaching, this should be the length of this entire curved path. This is the distance covered. The unit is meter. SI unit is meter. Whereas displacement is going to be the linear distance starting from the starting point to the end point. Linear distance means only the straight line distance, and the direction is going to be from start to end. So it's going to also come along with a direction as well. So that's the basic difference between distance and displacement. So one more thing that I'd like to tell you, I mean, one of the very simple example or common example that I usually discuss for this definition. If we have a circle, and if we have an object that is going around in a circular path, let's say an object is going around in a circular path in an anti-clockwise direction. So it's continuously going around this. Let's say this object, I'm gonna show this as a blue object. So let's say this one. Why is it not getting filled? Okay. So let's say this is the object that is moving around over here in an anti-clockwise circle. So let's say we are going to observe, we're going to start observing the particle's motion at a certain time. And usually for the case of physical observation, an ongoing happening can be happening for a pretty long time. And we start the time count at the instance the scenario starts getting observed. So let me say that again. The t equals to 0, which means that the initial time is always the instance of time when we start the observation of that behavior. Now that behavior or that change can be in terms of motion, it can be in terms of temperature, it can be in terms of nuclear division, it can be any physical phenomenon. But the moment when you start the observation is where t equals to 0. Let's say this is a circle, and let's say these are the two diameters that I'm trying to draw over here. Let's say these are the two diameters. And let's say the object starts from here at t equals to 0. So let's say we are starting the observation from here. Let's say after some time, the object reaches up at this position. So if I ask you, how much is the distance covered? That would be the arc length of this quarter circle. But if I ask you, what is the displacement of the object over here from this point? That has to be this thing. So this is the distance covered, this is the displacement. Let's say after some time, the object rotates further and eventually, let's say it comes to over here. I'm gonna choose a random point, let's say for example. When the object will reach over here after some time, so in that case, the distance covered would be the entire arc length of this much. This entire thing would be the distance covered, whereas the displacement in this case is gonna be the linear distance from the start to the end. So that's going to be our displacement in the direction from starting to end. So this is going to be our displacement, which interestingly tells us one more thing, that if the object eventually covers this whole thing and reaches all the way back to the starting position, let's say the object completes one full circle and comes back to the same position, and let's say it takes some time, which we usually say to be a time period. I'm going to get that definition later. But let's say the object completes one full circle and comes up over here. If the object comes to the same starting point, essentially the displacement of the object would be 0. Because when the object would have reached the exact same starting point, obviously, when the object would have reached the exact same starting point, the displacement would be 0, but the distance covered would not be 0. Because to make a one complete rotation around this circle, the object had to cover 2 pi r distance. Do you guys know this formula, 2 pi r? What does it stand for?
Circumference of a circle.
Circumference of the circle.
Circumference of the circle.
Circumference of the circle. Good. Can someone tell me what's the difference between circumference and perimeter?
Perimeter is the addition of boundaries.
Boundary lines.
True.
And
what is-
circumference is the
Addition of arc lengths.
Circumference is basically the curved line and the
curved line of the circle.
So let's say if I have so what you say, the circumference is applicable for a curved line and perimeter is applicable for straight lines. Is that the difference you're implying?
perimeter also.
No.
Perimeter also applies for curved line as well.
So,
The perimeter is
Yeah.
the boundary line.
It's a boundary line.
so can we not call the circumference of a circle is perimeter? Would that be
Obviously,
wrong?
we can.
Yes.
We can.
we
It is
can.
actually called the perimeter
Yes,
of a
sir.
circle.
Perimeter
why-
of a circle
why do
is the
we-
circumference.
So why do you use a different word, circumference? Or
It
why
is
can
a
we,
round shape.
In case of a semicircle, the curved part, we call it the circumference. But for the perimeter, we also include the diameter and the curved area, curved part.
so in other terms, we can what you can say. I really appreciate all of your information, and to be honest, all of you are correct. There was no wrong information that any of you produced, which I really appreciate. And for those of you who are confused and are not producing answers, please feel free to participate in that question. You can join in the chat, no big deal. So ideally, for a curved length, we can use the term circumference, and to be more exact, we use the term circumference for exclusively known circular arcs. If you have a parabolic path or a hyperbolic path, we don't usually call it circumference. For example, let's say an object has a shape that looks like this. Let's say an object has a shape that looks like this. You have this much over here, and let's say this is the part which is missing. Let's say we have this much part missing. So I'm gonna rub this off. And let's say this top part has a sort of a curved shape that might as well look like this. And you are told that this is not a part of a circle. So if it is not a part of a circle that you know for a fact, you will not say it to be a circumference. Circumference is usually exclusively used for parts of a circle. So exclusively circular জন্য আমরা তাকে circumference বলি। যেমন in other words, I can tell you is that the force by which earth pulls any object is called its weight. but the force by which any other things pulls any other object is called the gravitational force. So the exclusive gravitational force that belongs to Earth has a unique name. What is that name? Weight. So the gravitational force by which Earth pulls me down is called weight. The gravitational force by which Earth pulls the moon down is the weight of the moon at that position, and so on and so forth. But the force by which the sun pulls the Earth is not the weight of the Earth, is the gravitational pull of the sun on the Earth. So exclusively the gravitational pull of Earth has a unique name. We have given it a unique name. We call it weight. Something like that. That exclusively for circular regions or circular sections or circular arcs, we use the word circumference. For any other shape, curved surfaces but non-circular, we use the term perimeter. Beautiful. So, but if you think in case of in terms of essence, they basically both represent the same thing. So the getting back to the actual definition for distance and displacement, that when the object would have covered one full circle and reached to the same position, it would have covered a total distance of 2 pi r. So I'm going to write the distance over here like that. Whereas the displacement, which can be written as a vector quantity, vector quantities can be written in 3 different ways. If you're handwriting it, you can give a single bar sign onto it, representing it as vector. Or some books also use it like this, using an arrow in this fashion. That's also another way to write this thing. In case of printing, we can use either of this term, or there is another version that we can do. We can write that vector quantity in bold letter. Let's say D. So let's say small d. So if you write that into bold letter, that can also work as your vector sign. So vectors can be represented in 3 different ways. So in this case, I can say that the displacement that this object have made whenever it has completed one full circle, that would be essentially 0. So in a circular path, after completing full circular paths, the displacement made by the object would be 0, because the idea is very simple. The displacement was defined as the linear distance from the starting point to the end point in the direction from the starting to the end point. So because the object reaches up to the same position, the total displacement would be 0. Do we understand this whole idea about distance and displacement? Are we clear about this
Yes,
example?
Yes,
Yes,
sir.
Sir.
The next thing that we're going to cover is going to be speed and velocity, which is also pretty simple. In many cases, we use these two terms equivocally. Equivocally means alternately or replaceably. I'm not sure if replaceably is a word, which I'm using quite a lot over these online courses. But I hope it's a word. Is it a word? Replaceably is not a word. It's not a word. Okay, anyway, it's a replaceable word. So, but in actual case, there's quite a difference. Speed is the scalar quantity, whereas velocity is the vector quantity. So, speed is only the magnitude, and velocity is magnitude and also direction together. One of the reasons that we can use these two terms as alternate words in cases, because of couple of advantage or a couple of less complicacy that we have to work with in our O-level scenarios. Let me tell you this thing very specifically. Before I just get into the velocity part, I'm going to define the term acceleration as well. Acceleration is essentially a vector quantity. It doesn't have any scalar form. Acceleration is written as change of velocity over a change of time. I'm only writing the formula over here, not writing the whole definition, because the definition is basically the description of this formula. So we can say acceleration of an object is the rate of change of velocity. Now you should remember this couple of words. In physics, I know for physics, I'm not sure about other subjects. The word rate always means something divided by relevant amount of time. So rate means the change of something with respect to time. So you measure the change of a certain quantity over a duration of time, then you divide that change by the time amount, you get the rate of the change. So acceleration is the rate of change of velocity. Power is the rate of change of energy or rate of change of work done. and you can essentially have a lot of other of this variation, which also work with rate. A similar word that we are gonna eventually come across in our syllabus is the word specific. Whenever I use the term specific, specific means the amount, some certain amount with respect to mass. So for example, we can have specific heat capacity. We can have specific latent heat of vaporization, or specific latent heat of melting. We can also have specific charge. We can have what other specific things can we have? I cannot think of any other. But the word specific essentially means the something divided by mass, whereas the word rate means something that is divided by time. So acceleration is basically change of velocity over change over time. Now comes the big idea that in your syllabus, for the most part of our mathematical calculation, not for theory covers a bit more. For the most part of our mathematical calculation, in most cases, let's say in 80% of the cases, we're going to be working with scenarios where an object is going to move in one single straight line and pretty much in the same direction. That's going to be most of our working. So either the object might decelerate, the object might accelerate, or it might have different values of acceleration or deceleration. But for pretty much the entire duration of its motion, is going to move in the same direction. I mean, it can stop, but for most math, it is not going to revert direction, which means if you use the term speed and if you use the term velocity for a scenario where the direction of motion is actually not being changed, they can be used alternately. I mean, if I say, let's say if I'm saying that an object is going to travel from point A to point B, but it is going to do this kind of changes of velocities in its path at this time instances. So I can say this, but as long as I define that the object is going to travel from A to B always, which essentially tells me that at any case, the object is always going to move to the right, or it might be stationary, but it's not going to move backwards. If it is evident from your question, then speed and velocity would pretty much mean the same thing. Because if I say that at this position, the speed of the object is 15 meters per second, well, essentially it also means that at this point, the velocity of the object is also 15 meters per second in the direction from A to B. Yay. How about I do not disable the annotation. Rather, I turn on the option that whenever any of you will annotate unnecessarily, your name is going to pop up beside that. For example, Swadip Shakar just did an annotation right now, and he did another one. So other than stopping you doing that, I detect who is doing that. So you can actually do an annotate over here. Try that.
I say my sister. Sorry, sir.
Okay. Just be careful to be careful. That's all I'm saying. You can annotate, but I'm gonna see who are you that is gonna annotate. So suit yourself. So since the object is knowingly traveling from point A to point B, we can essentially say that the speed of this object at this point is very much the velocity of the object, because we know from an earlier description that the object is essentially moving from left to right. So speed and velocity can be alternately used for these kind of scenarios. This is one of the important part that I want you to understand. Another thing that is really important for you to understand is that if in cases the object can possibly revert its direction. Now, for horizontal scenarios, this is not very common for us. For horizontal scenarios, this is not very common for us. It can actually happen. In what kind of situation it can happen, I'll tell you. But it's not very common for horizontal scenarios, but it is very common for vertically thrown objects upwards. Think about it. If you throw an object vertically upwards, then the object is going to start going upwards as it leaves from your hand. So we are doing the time count as the object leaves from your hand. So it means the object has some initial velocity upwards, but since it's going to go against the gravity or in the opposite direction of the weight, it's going to slow down. So it's going to rise up, and eventually at one point it's going to come to a momentarily stop. For an instance, it will stop, and then it's going to start falling down. we discussed in length for that. Why do we feel like that it comes to a stop and it stays over there for a short amount of time and then it starts falling? This actually doesn't happen because of the shortcoming of our visual system. Our brain holds the image of an object for 0.1 second in our brain. That's why it apparently feels to us that the object gets stuck at the highest position for some time and then it starts to fall down, but that's not the case. The object rises up, stops, and immediately starts to fall downwards. So in this case, there can be a change of velocity. Now, one of the key part that I need to understand, if an object is thrown vertically upwards, try to understand this example very carefully. Let's say here is an object. If an object is being thrown upward, let's say I tell you that the initial velocity of the object was, let's say 10 meters per second. 10 meters per second? Okay, let's say 20 meters per second. Now, one thing is very important. As the object will go up, the acceleration of the object is going to be working in which direction? Is the weight going to work upwards or is the weight going to work downwards? Think about it. In which direction will
Weight
the
is
weight
going
work?
to act downwards.
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 Will definitely and always going to work downwards. Beautiful.
ডাউনওয়ার্ডস এ হবে, এটার কারণ আছে না স্যার? ডাউনওয়ার্ডস হওয়ার জন্য মানে কেন হবে ডাউনওয়ার্ডসটা?
Because the earth pulls every object
না,
towards the
গ্র্যাভিটি
center.
কারণে, ইজ ইট
Yes.
বিকজ অফ গ্র্যাভিটি?
Yes.
আর যদি মানে মনে করেন মানে স্পেসে মানে বল ফেললাম তাহলে কি চেঞ্জ হইতো? মানে স্পিডটা কি মানে বাড়তে থাকতো, মানে ওয়েটটা কি উপরে যেত নাকি?
It would have flowed.
নো ওয়েটে ম্যাটার হবে না।
বলতেছি
কিশোর তো নাই ওয়েটের ওকে অ্যাট্রাক্ট
উপরে
করার জন্য।
attract করার জন্য, exactly.
বলতেছি
এসে যাওয়ার পর আর থামতে হবে না, ওখানে চলতে থাকবে।
It's gonna float, exactly.
আমি বলতেছি
থামানোর কেউ নাই।
your reactions are absolutely valid and they're correct, but there is more to what you are saying. So I'm gonna cover the whole idea of weightlessness and how do we sense weightlessness in a bit. ঠিক আছে, আমি আজকে ক্লাসে বলবো, don't worry about that. So I'm gonna cover that after a little bit. So I'm just a definition গুলো একটু বলে নেই, then I'm gonna essentially cover the weightlessness scenario. So
You already showed a video regarding
weightlessness.
weightlessness. Sir, you posted a video.
So what did we discuss in that class?
Not in the class. You posted in the messenger group about
Oh,
weightlessness.
স্যার দেখি নাই তো।
The physics girl.
Yes, sir, the physics girl.
Okay, yeah, that was a video, but I didn't explain. So I'm gonna explain. I'm gonna give you my version of explanation anyway. So for the time being, let's consider that this is happening on the surface of the Earth. This object is gonna be pulled downwards because of its weight, because of the gravitational pull of the Earth. So let's concentrate on what is happening on Earth. We're gonna go into space a bit later, but I will go there. Don't worry. So as the object is being thrown upwards, we're considering the upward velocity as 20 meters per second. So if I don't want to give a minus sign over here, which means placing the value of initial velocity, not speed, initial velocity as positive as 20 meters per second, because I'm not giving any minus sign over here, means by default there is a positive sign, this is a positive number. It means in this scenario, I'm considering upwards direction to be my positive direction, which means because the weight of the object is going to work downwards, let me just show that weight by a large arrow. Let's say that weight is ground. So because the weight, why am I always choosing second color? Because the weight of the object is always going to fall downwards. Is it okay now? Yes. Because the weight of the object is always going to work downwards. So in this case, as the object rises up, the acceleration should be considered as negative. See if it makes sense. Because acceleration is also a vector quantity, initial velocity is also a vector quantity. If you consider this thing to be 20 meters per second, then the acceleration should not be 10 meters per second square. It should be minus 10 meters per second square. See if it makes sense. Any vector quantity, if it's considered to be upward as positive, so all the vector quantities that will work exactly in the upward direction will have a positive value. All the vector quantities that works exactly in the downward direction will essentially have a negative value. So that's essentially what I'm trying to highlight here.
If we throw a ball at 20 meters per second square, the 20 meters per second, then it is also, if it accelerates in the upward direction,
We'd say decelerate.
it will, if you throw a ball and then it doesn't maintain a constant speed or velocity, it is accelerating, then
It
there
is
will be two
accelerate.
acceleration.
It is accelerating, but that would be negative acceleration. Well, in general terms, acceleration means change of velocity. So to be honest, speed increase is also acceleration. Speed decrease is also acceleration. Exclusively decreasing speed is called deceleration. So if you throw an object upwards and the object accelerates downwards because the weight is working downwards, in that case, the object will not immediately start to come downwards. It is going to slow down as it goes up. It is going to slow down as it goes up, and it is going to decelerate.
Sir,
Yes,
why it goes up? Why is it decelerating? It should accelerate, right?
because Earth's pulling is down.
Sir, not of the Earth's gravity. Just
Building-
if you throw a ball upwards and it doesn't maintain a constant speed, it will accelerate, right?
Yes,
Like 20 meters per second more than 20 meters per second and 30 meters per second. If it
no,
does like that, then
not
it's
30, not 30. Because if it has to be 30, the object has to experience a force in the same direction of its initial velocity. That's the point that I'm trying to make. That if you have an if you
okay.
have an upward velocity and if you have an upward acceleration, this upward acceleration will slowly add up to that initial velocity. That's how your
Okay,
speed
sir.
increase. But in this case, the acceleration is working in the reverse direction, which is gonna slow down your velocity. Or in other words, if I just break it down for you, which can make better sense to many of you, you got my point, which I appreciate. But I'm gonna go for a bit more discussion. For example, if I write the acceleration as minus 10 meters per second squared, that's the acceleration. One of the easier way to make sense of 10 meter per second square is like this. This can be written as like this: 10 meter per second per second. Now, this writing the meter per second square in this fashion can give you a much better visualization of what does meter per second square actually mean. Meter per second square essentially mean meter per second per second. It basically tells you how much the velocity is gonna change every second. How many meter per second changes? How many meters per second change happen every second? So if your object has an acceleration of 10 meters per second square, it means the amount of change of velocity or initial velocity will be 10 meters per second. Now, if it is in the same direction, it's gonna get added up continuously. If it is in the opposite direction, it's gonna get decreased continuously. For example, if I go ahead further for this problem, if you throw this object 20 meters per second, it's gonna rise up. After the first second, it will experience a reduction of 10 meters per second velocity because this is 10 meters per second per second. So after 1 second, the velocity is going to be how much? You subtract 10 from 20. What do you get?
Minus 10.
Minus 10.
You subtract 10 from 20.
Minus 10.
10, 10.
You hear me again. You subtract
10, 10,
10
10.
from 20.
10. Sorry.
10, 10, 10.
Sorry. 10.
You have 10 meters per second. What this means that you threw the object at 20 meters per second upward velocity. As the object is going upwards, it's gonna slowly lose its velocity because the acceleration is working downwards. Over a duration of 1 second, I can pretty much write 1 second over here just to make my point. Over a duration of 1 second, the velocity is gonna experience a change of minus 10. So after 1 second, the velocity will be 20 meters per second minus 10, which is 10 meters per second. After another 1 second, that final velocity can become 0. Which means if you throw an object at exactly 20 meters per second in the vertical upward direction, the total time to rise up is gonna be 2. Right?
Sir, I didn't understand.
Sir, I didn't understand.
Sir, I didn't understand also.
I'll make point. See if it makes sense. The velocity at t equals to 0 is what we say initial velocity, which is denoted by the symbol u. We are throwing the object upwards at 20 meters per second. So the object starts to go upwards. And because the acceleration is working in the opposite direction, it is gonna experience a change of minus 10 meters per second every second, which means after every 1 second amount of time, the initial velocity is gonna get a reduction of 10 meters per second because the object is being pulled downwards. So you had a positive 20 meters per second velocity, initial velocity. After 1 second, that velocity will have a reduction of 10 meters per second. So that's why if you do that, 20 minus 10, because the change of velocity is going to be 10 meters per second.
After 1 second.
Yeah, after 1 second. I meant it as 1 second. So 1 second, not 15, 1 second. That's what I mean by t equals to 1 second. T equals to 1 second means after 1 second. So here's your time instant starts. 1 second passes by, and after 1 second, its final velocity is gonna be 10 meters per second. It's gonna have 10 meters per second remaining because this subtraction gives you 10 meters per second. Because every second you're gonna be losing how much? 10 meters per second. I'm using the word losing. Why?
It will decrease in velocity.
It will get a decrease in velocity because in this case the upward velocity is positive and the downward acceleration is considered negative. Actually, let me just finish this part by discussing the falling part, then it might as well make better sense to all of you. So this is going to happen, and then after a 1 further second, this 10 meters per second which we had, it is going to reduce by another 10 meters per second. So the final velocity is going to be 0 meters per second. Since the final velocity over here is 0 meters per second, this is basically the maximum highest point of the rise because the object has come to an instantaneous rest. So what is going to happen beyond this point? The object has reached up to its highest point. Is it going to get stuck over there, or is it going to start falling downwards back naturally?
Falling downwards.
It's going to fall downwards. Now there is a catch. If the object is going to start falling downwards, in that case, this velocity and this acceleration, they are going to both work in the same direction. Now there are two different ways we can approach. We can process this problem. One of the approaches that we can consider this positive direction of velocity, positive direction of vector as an intact information. Intact information means everything that is upward vector is positive, everything that is downward vector is negative. If we want to maintain this would mean as long as the object was rising upwards, it was having a positive velocity because it was working in the upward direction. But whenever the object is going to start falling downwards, that velocity should not be positive anymore, because if upward velocity is positive by the idea of vectors, downward velocity should be what?
Negative.
Sir, I have a question.
Yes.
Sir, first of all, my question is why does it experience an acceleration while it goes down, and then again negative acceleration? Why is that? Sir,
Yeah, I got your question. I'm trying to think of a way to make it sense better. I'm trying to think. Wait.
Sir, can't we consider the downward direction to be positive?
We actually can, but in some cases we shouldn't. I'll tell you about this. Wait. Okay. The question
Sir,
that
sir, doesn't negative acceleration mean deceleration?
Yes, it does.
So it basically experiences deceleration while it goes down, right? But why do we say acceleration and more of a negative?
Beautiful question. I'll tell you. Because in our syllabus, we're gonna mostly work with a singular direction. Mostly we're gonna work with a singular direction. For your syllabus, this term almost specifically means, I'm using the word almost because there can be exceptions of this rule. This always means speed up. And deceleration in almost in all cases, this means slow down. So if in scenarios where your object actually slows down, we call that deceleration. I could actually explain this thing much too easily if I used a formula, but I really don't want to use the formula right now because I want you to physically understand what is happening. I'll go again. The whole idea that I'm trying to explain, the example that I'm trying to explain over here is based upon the idea that we are considering upward vectors as positive vectors and downward vectors as negative vectors. First, appreciate this information. Upward vectors as positive vectors, downward vectors as negative vectors, which means if you have two vectors working upwards, you're going to add them. If you have one vector working upwards and another vector working downwards, you're going to subtract them. First, appreciate this information. Same directional vectors would be added. Opposite directional vectors would become subtracted. Can we appreciate this much?
Yes, sir.
Yes, sir.
This is okay. So what I'm trying to show you over here, that when the object is being thrown upwards and also when the object will also fall, but let's consider the upward motion first. For the upward motion, the acceleration of gravity is working downwards. So if I am, because I wanted to consider the upward direction as a positive direction for all the vectors, I wrote the initial velocity as a positive velocity, which is 20 meters per second, because I considered upward direction as positive. Because acceleration due to gravity is working downwards, that's why I had to write this as minus 10 meters per second squared. That's what I'm trying to get in your head. So
Sorry,
for the
this-
entire, let me finish. For the entire rising part, the upward velocity is gonna work upwards. So that's gonna be an upward vector. But for that entire duration, the acceleration is gonna work downwards, which is gonna be a negative vector. So you cannot add these two numbers, or you can add these two numbers considering one of them to be positive, the other one can be negative. That's essentially what I did over here. After 1 second, the amount of change of velocity is going to be 10 meters per second, because that's what this whole thing means. That's what this breakdown of this unit means. 10 meters per second per second. The amount of change that the acceleration will bring to the object speed, that it will be reduced by 10 meters per second every second. So what this means, that over the duration of this thing, over the duration of this 1 second, I mean 1 second is actually amount of time, it's not an instance of time, it's a total duration of time. Over the span of this 1 second, this initial velocity of 20 meters per second is going to reduce to 10 meters per second. Why 10 meters per second? Because this 20 meters per second is going to be reduced by 1 second worth of acceleration. See if it makes sense. 1 second worth of acceleration. Now, how much change would you have to initial velocity in 1 second? That is 10 meters per second. In which direction? Downwards. So you can either think this as 20 minus 10, because they are working in opposite direction. The object is going upwards and the acceleration is working downwards. So that's why you're subtracting them. Or I could also write it like this: 20, you can add both of these, but one of the vector is a positive vector, the other one is a negative vector. So if you do this, that also basically ultimately also gives you what? 10 meters per second. That's why we are saying in this case the object is decelerating, because the acceleration is working in the opposite direction of the initial velocity, which means the object is essentially slowing down. And slowing down is referred to as deceleration. বুঝা গেছে কি?
Sir, is it that it slows down while it goes up?
Yes.
Okay, now I understand.
Think of a regular scenario. You throw an object in air. What happens? Does the object keeps on traveling and eventually reach up to the space, or it eventually comes back?
It comes back.
So if it has to come back, it essentially means what? That
It needs to slow down.
It has to slow down. It has to slow down to a stop, and then it has to start its journey downwards so that it can come back.
Okay,
Yes,
so sir,
yes.
so sir, when it comes down, it speeds up.
It definitely speeds up. That's what I was trying to go in the second part, but which I could not reach because I was answering questions. Yes, Saptoshi.
My question is that naturally when an object is thrown upwards, what is the factor that influences how much height will it be covering?
Potentially speaking, there are three factors. The very first factor is how much speed are you throwing it by. Initial speed. If you throw it with a really big speed, it's gonna reach to a really large height, and vice versa. The second factor is what is the exact value of acceleration due to gravity at that location of the Earth. Because we use a standardized value of 10 meter per second square downwards for the value of acceleration for all of our mathematical endeavors. But to be honest, the value of Earth's acceleration is not same everywhere, specifically on every different position. This is due to the shape of the Earth, because Earth is not perfectly round. It's a bit squashed at the poles. So and also the other reason is the axial rotation of Earth around its own axis, that also do some effect on the gravitational field value. So,
Also the mass.
Earth's mass is not a variable.
No, the object's mass.
Object's mass is not relevant for its acceleration. Object's mass will control its weight value, but it will not control its acceleration. So what I'm trying to mean you is that if you throw a 1 kg object vertically upwards at some initial velocity, if you throw a 2 kg object upwards at some initial velocity, both of the objects, irrespective of the initial velocity, irrespective of their mass, they are gonna both be subjected to the same value of gravitational acceleration. But the one that has a bigger mass will have a bigger weight. The one that has a smaller mass will have a smaller weight. But the acceleration will be same for both of them.
But the height, if we throw them at the same velocity, then one of them will reach a higher height, greater height.
Not essentially. Because mass doesn't have to deal with kinematics. Mass has to deal with forces.
Okay, sir.
I'll tell you this in a bit. Jara haturase to wait koro, I'll take your question. So the point I was trying to make, that this is going to be happening over this duration. So I really want to finish the discussion that I'm going to go forward, and then I'm going to take the rest of the questions. So once the object reaches up to its maximum height, the object is going to start falling downwards. So as the object is going to start falling downwards, I can essentially go ahead and do this calculation that what is happening to the object's velocity as it falls downwards. Now, one of the ways that we can consider that, because in the falling duration, in the falling scenario, I mean, there are two different ways to do the calculation. Because the object is falling downwards, we can consider the final velocity should also be negative. Or we can consider, because in this case, the falling velocity direction and the acceleration direction, they are both in the same direction, this object is going to speed up. So we can in generally consider both of these things to be positive. So I'm going to show you the second method first. So because for the falling scenario, the velocity direction and acceleration are going to be positive. So other than writing this as a negative value, I'm going to write both of them in the same direction. I am giving you some trouble. I'm willingly giving you some trouble with the direction factor for the vectors. Other than only going for speed up and slow down, I could have only told you that for acceleration cases, use a positive value of acceleration. For deceleration cases, use a negative value of acceleration in the equation. I could have told you this, but that doesn't necessarily help you to get you a good idea of direction implication. That how does the direction of a certain vector affect the other relevant vectors? That's why I'm not telling you to directly go for the shortcut of choosing the plus or minus sign based upon the context of the question. I want you to understand the idea of the direction properly. So when the object is going to start falling downwards, both the downward velocity and the downward accelerations are going to work in the same way. So I'm going to consider both of them over here. So just to make this math a bit more interesting, I'm going to calculate this thing as, let's say, a small fraction. Say how much is going to be the velocity of this object at t equals to 2.5 seconds. So I'm not using exactly 1 second. I'm using 2.5 seconds. Now I want you to appreciate what is happening. Try to understand what is happening over here. At 2 second mark, the object reached its maximum height, where the final velocity was 0, which means the object is currently at maximum height. But whenever the object reaches maximum height, it will definitely fall downwards, because the weight of the object did not stop working on the object as it reached its maximum height. If it did stop working, the object should have got stuck in that position and never come down. But that doesn't happen. The object eventually comes down, which means even at the highest speed, the object does have acceleration. It has zero velocity, but it can have acceleration. Now, some of you might wonder, that doesn't even sound right, because how could possibly a rest object can have acceleration? Well, rest objects can have accelerations depending on how the object came to its rest position. Depending on how the object came to its rest position. So the reason or the mechanism how this rest position was achieved can affect whether acceleration is going to work on the object or not. So when we throw the object vertically upwards for the entire flight duration, going up, stopping, and coming down, weight is always working on the object without any hitch, because the mass weight comes from the property of the mass of two bodies. Here, one of the object is the Earth, the other object is the object, the other one is the object that we are throwing in the upwards. So because both of them will always have mass, I mean, it is not possible that at one point of its motion, one of them is going to have a reduced amount of mass. That simply doesn't sound right, and that is not correct. Since both of them are going to have their masses intact, so they are always going to attract each other, and the acceleration due to gravity would be present at every instance of the motion. So as it is going upwards, it has a value. As it stops, it has a value. As it comes down, it has also the same value. So acceleration due to gravity is not dependent on velocity. Acceleration due to gravity is dependent on the force by which the two objects attract each other. And the way gravitation works is because of the virtue of mass of objects or multiple objects. So the object is still going to be under some acceleration as it goes upward. So if the object now starts to fall at time t equals to 2 seconds, here I'm trying to calculate what would be the velocity of this object after 2.5 seconds. Have a look. How much time has passed over here? Half second. Now, other than doing any, half second from the highest point. T equals to 2.5 seconds means the object is going to start falling from this point. So for how long did the object fall down? The object did fall down for half a second.
Yeah.
Half a second. Because this 2.5 seconds means this is the 2.5 seconds starting from all the way from the initial time. But I'm trying to tell you that how much time is this from the instance of reaching the highest point. এখান থেকে এই টাইমটা কতটুকু সময়? 0.5 seconds. Now have a look over here. Without using your calculator, try to do this math in your head. This equation means, if you have questions, please raise hands. This equation means that every second the velocity of the object is going to be undergoing a change of 10 meters per second. So 10 meters per second per second. 10 meters per second per second. So that would be the amount of change. From here to here, the amount of time that actually passed was half second, which means this half second will produce half this amount of change to this velocity. Akem Sami, you just put a dot over here, right over here, and then we just erased it. Do you need any help?
Yes sir, মানে আমার ভয়েস আপনার ভয়েসটা একটু কাটা কাটা আসতেছে, তো আপনি আবার একটু বলতে পারবেন যে কি বলেছিলেন?
Oh, what I said is that from t equals to 2.2 seconds to t equals to 2.5 seconds, the amount of time that has been passed is 0.5 seconds. Now have a look at this expression and try to do this math in your head without using any formula. How much change should this acceleration value bring to the initial velocity within a duration of half second? 10 meters per second means 10 meters per second changes happen every 1 second. So how much change happens in half second?
5.
It's 5.
Yeah.
It should be 5. Can every one of you agree to this?
Yes, sir.
Within a duration of 1 second, the amount of change that the acceleration brings to the velocity is 10 meters per second. So within half second, the amount of change should be 5 meters per second. Now, so because of this, the amount of change of velocity over here should be 5 meters per second. So what should be your final velocity at this point? This should be the initial velocity from this point, which is 0, plus 5 meters per second. So how much do you get? You get 5 meters per second. So after 2.5 seconds from the very beginning of time count, which was the instance of throwing the object vertically upwards, after 2.5 seconds, the velocity of the object would be 5 meters per second downwards. What about if we,
Minus 5 meters per second.
exactly.
Sorry, isn't it going down? So minus.
Exactly. We should give this as, because we are now defining this as a vector, so we should be preferably give a minus sign over here. I haven't yet discussed the equations of motion with you. When I'll discuss it, you will get the idea of this -5 pretty well. But since many of you are bringing this up, and I really appreciate this, that since we consider upward direction as a positive vector, so the downward velocity should be represented with a negative vector. Now, one thing that I really want you to appreciate, try to have a very good look at the signs and try to appreciate the answer. Many of you might feel like, sir, what are you doing? 0 plus 5 equals to -5? What the hell? Well, here's the deal. I should have written 0 plus -5. Why?
Because it's acting down.
Yeah.
Because this change is working in the downward direction. Downward vectors should be represented as negative vectors. Now, this is the part that I really want you to appreciate. Try to understand. This object is now accelerating in the downward direction, which is the same direction as the acceleration. The velocity and the acceleration both have the same direction. So like I said, that if both velocity and acceleration work in the same direction, we will add their values. So have a look here. What are we essentially doing here? We are adding 5 downwards with 0. So we are getting -5. So what if we try to extrapolate this problem for another fraction of second? That is going to be a bit different. Let's say I want to calculate the final velocity after t equals to, let's say, 3.1 second. Not exactly 3 seconds. If I want to calculate this thing for 3.1 second, try to have a look. How much time has passed from here to here?
0.6 seconds.
0.6.
From here to here, the amount of time that has passed is 0.6 seconds, which means this 0.6 second, not meter, this 0.66 second, which means this final velocity will experience a change that is gonna brought about to this value within a duration of 0.6 second. So how does that work? Pretty simple. Sorry. So how does that work? Have a look. If you have a look at this equation once again, this equation tells you what I'm gonna write this information over here for your better understanding. In 1 second of time, the change of velocity, I can write delta v, that is equals to 10 meters per second. See if it makes sense. In 1 second of time, the change of velocity happens is that is 10 meters per second square, and that is downward. So I might as well give a minus over here, just because of the direction. Which means that if we have 0.6 seconds, so that is 0.6 over here, how much would be the change of velocity?
Sir, can you please repeat?
If you,
Minus
I mean,
11.
-6.
6, yeah.
it should be -6, yes. So the question that I asked is that 1 second of time brings about a change of 10 meters per second velocity to the 10 meters per second of change to the initial velocity. My question was, we could very easily calculate the 5.5 ratio because we can. It works pretty well. But if I want you to understand that if I try to find out the change of velocity over a duration of 0.6 second, in that case, how much would be the final velocity? So within a 0.6 second, the change of velocity from this equation is going to be how much? -10 into 0.6. How much should you get? -6.
-6.
-6.
You're going to get -6, which
-6.
means now this velocity is gonna undergo a change of -6. So I might as well write this. So I'm gonna write -5, and I'm going to add the change of -6 to the initial value. How much do you get?
-11.
ঠিক আছে? Eventually all the way, acha, so এই পর্যন্ত আমি calculation করলাম. I'm gonna go a bit further. I'm gonna show you one more step, and then I'll start taking your questions. That is, if you have a look over here, from start to the highest point, how much time was taken? It was 2 seconds. Within a duration of exactly 2 seconds, the object did rise up to its maximum height. We are essentially considering area is negligible over here, so disregard that. don't cloud your judgment with air resistance. It's not never gonna be a part of your calculation up to your all levels part. It's not gonna be. So the object did rise to its maximum height within a time amount of 2 seconds. So symmetry should tell us if the object drops back to the earth, how much time should it take? Another 2 seconds?
Yes.
Yes, sir.
যতটুকু উঠতে যতটুকু টাইম লাগবে ওই সেম ডিসটেন্স ফল করতেও ততটুকুই কি লাগার কথা, টাইম লাগার কথা। So if I go ahead and try that, if I try to find out the total distance covered after t equals to 4 seconds, which is double of 2 seconds, then how much should I get? Now have a look. From here to here, how much is the change? How much time has elapsed from this point time instance to this time
0.9.
instance?
0.9.
That is 0.9 second. Beautiful. That is 0.9 second. Nice. And this 0.9 second will bring about a change of how much? If you look at this equation, that one koi liklam. That 1 second of time, 1 second duration of time gives us a delta v of 10 meter per second. So how much delta v should we have in 0.9 second?
9.
9.
In 1 second you get minus 10. So in 0.9 second you're gonna get 9. You just do the multiplication in unitary method, which means now the total amount of change we're gonna have is minus 9. So I'm gonna change this thing over here. So v is gonna be, this thing is gonna be changed over here, minus 11 plus minus 9. How much are we getting?
Minus 20.
Minus 20 meter per second. Now you see, this is the beauty of math. Have a look. At which speed did we throw the object upwards?
20 meter per second.
We threw the object vertically upwards at 20. Arik, তোমার চ্যানেল থেকে প্রচুর নয়েজ আসতেছে। We threw the object vertically upwards at 20 meter per second, and after 2 seconds it came to the highest point, which was at 0. And after another 2 seconds, which means at t equals to 4 seconds, the object actually reached the same amount of velocity at the only in the opposite direction. So these are the type of questions that you might have to actually have to work with, where you might have for vertically thrown objects towards the sky, we can have this kind of problems. I did not show you any math or any equation over here. I actually basically use the concept of acceleration to do all of this math. But my question to all of you, did this working make sense to you?
Yes, sir.
Yes.
If any of
Yes,
you have
sir.
any relevant question, you can raise your
No.
hand. I'll take your questions one by one.
Yes, sir.
Yeah, Arif, you have a question. You raised your hand quite a bit earlier. Yeah, please go ahead.
ইয়েস স্যার, যে মানে বল ফেলা যে এটা নিয়ে স্যার, মানে এটা নিয়ে মানে এটা কোশ্চেন হলো কি স্যার, মানে যদি মনে করেন একটা কম ওয়েটের জিনিস স্যার, মানে যদি উপরে ফেলায়, মানে অনেক সময় দেখা যায় যে ওই কম ওয়েটের জিনিসগুলো না স্যার ফ্লোট করে, মানে এগুলো মানে কোনো মানে ডাউনওয়ার্ড আপওয়ার্ড ভেলোসিটি এসব কাজ করে না।
আচ্ছা, কম ওয়েটের জিনিস হলে
মানে
আমাদের
ফেদার বলতে পারেন, ফেদার।
হ্যাঁ বলতেছি, কম ওয়েটের জিনিস হলে আমাদের ডাউনওয়ার্ড আপওয়ার্ড ভেলোসিটি কাজ করবে, বাট ওইখানে আমাদের কিছু অ্যাডিশনাল কিছু ফ্যাক্টর আসে। সেটা হচ্ছে যে এয়ার রেজিস্ট্যান্স গুলো তখন আর ওয়েটের তুলনায় নেগলিজিবল হয় না। আমি একদম ফার্স্ট বা সেকেন্ড ক্লাসে মনে হয় আমি তোমাদেরকে দ্য আইডিয়া অফ নেগলিজিবিলিটি বুঝাইছিলাম।
হ্যাঁ,
যে whenever we have multiple comparable things, if we have one thing or one or two things which are extremely small compared to the other relevant things, we can consider those very small things to be negligible. So what happens that for really heavy objects, for example, let's say steel ball, metal ball, for this kind of objects, the air resistance is negligible compared to its weight if you drop them from a short height. But for feathers, it is not. Acha, I'm gonna get your question in a bit. আমি এটা ডিটেইলস আলাপ করব। So okay, further আমি এই question একটু পর ডিটেইলস আলাপ করতেছি। Oyetri, do you have any question from this part of the calculation?
Sir, I had a question about the why -5 meter per second লেখা হচ্ছে, like সবকটার সামনে একটা মাইনাস সাইন আসছে. I guess I missed that part out.
Oh, that's pretty simple, because for this entire math to work out, I considered upward directional vectors as positive vectors. That's why I wrote in this box.
Oh, acha, thank you.
So as the object was rising upwards, all of these velocities was written as positive velocities, 20 meter per second, 10 meter per second, and then 0 meter per second. But as the object was falling downwards, we represent all of those velocities as negative velocities because we are trying to represent that upward is considered positive, so downward velocity should be as a vector quantity. Because it is a vector quantity, that those minus signs should represent the reverse direction, which is downwards. বুঝা গেছে?
Yes, sir, বুঝেছি.
আচ্ছা, yes, Fabi Harim.
Sir, I didn't understand how we got -6 and -9.
Which one?
I don't know. I didn't understand how we got -6 and -9, and like, you know, the one you just showed us, the calculation, -6 and -9, -5 plus -6.
Oh, this one?
Yeah.
Oh, this was because the amount of time that was elapsed from t equals to 3.1 second to t equals to 4 second is 0.9 second. So this information meant that 10 meter per second change within 1 second of time. So if you use 0.9 second of time, how much change should you have? That should give you a delta v of how much? 10 into 0.9, that gives you minus 9 meter per second.
Oh.
That's what we need to change over here.
Oh, okay. Yeah, I understood.
Sure.
Yes, sir.
I'm gonna give you all the formula, which is gonna make the working of this math pretty simple. But I mean, it is important that you understand how the math works. This is basically the step-by-step process to give you some idea how the math works. I mean, judging the equation, locating the variables, and placing the numbers in your equation and be able to calculate out the answer is essentially a good skill, mark scoring skill, which is required because you'll be judged upon that. But you also need to understand inherently what is happening to the object. That's why I went through all of this trouble. Many of you might not like this process, but I prefer to teach it this way for the very first time to make a good understanding of how the acceleration actually affect the velocity. So the next point that I'm gonna discuss at this point of time, we're gonna take a break after 5 minutes for prayer. But I'll take 5 minutes. Yes.
So when are you going to answer my question?
After a while.
Okay.
It will show up in certain part of my lecture, and once I get past this point, I'll refer to you. Don't worry.
We're going on a break of 5 minutes.
বুঝি নাই?
Sir, are we going on a break of 5 minutes?
After 5 minutes, we're gonna give a break for prayer. After 5 minutes. So listen to me pretty close. One of the things that you really need to understand is that any object can have a certain amount of force available to itself because of some physical interaction from the outside. It can only spend specific part of this force, or maybe all part of this force, to one cause. It cannot use the same amount of force for multiple purposes. Now, what do I mean by this? Let me give you a very simple example, which is a small MCQ question that pops in your AS level, but it's a very good example. That's why I'm picking this up. Let's say here we have a ground that is frictionless, and we have two objects. I meant it to be touching the plank, but it didn't happen. Disregard that. It is on the ground, not floating. Let's say we have two objects over here, and these two objects are these two. So this is our object X, this is our object Y. Now, try to understand very clearly. Let's say the mass of object X is 3m and the mass of object Y is m. They are in contact. Now, if I apply a force of F over here, if I apply a force of F on the objects of this side of the X, how much force will the object X exert on Y? That's my question.
Its force, including the force which we exert. 3m plus the force we exert.
All right. কি বলছে আবার আমি খেয়াল করি নাই
3m plus the force which we are exerting.
Well, one thing you need to understand is that you cannot add dissimilar quantities. You cannot add mass with force. You can add two masses. You can add two forces. You can add two accelerations. You can add two velocities.
Just the force that we add, I guess.
It's just one. Either in the voice channel or in the chat channel. Give me some response. How much force do you think will X exert on Y?
F.
That's one response.
So can it be the weight acting on X plus the F?
Sir,
Well,
F.
the F force is perfectly horizontal. They might be, they are subject to their weight, but the weight doesn't have to do anything over here because I define the surface to be frictionless. So the weight is not essentially playing any role because I'm applying the external force horizontally. Adiba Amira Siddiqa, you wrote one thing that is correct, but that's not a value. I would like to have a value. What you wrote is an output of Newton's third law, which is very smart and correct response. I appreciate that. But what would be that value in terms of the F number?
F.
Okay. I'll help you to sort this out. I'll help you to sort this out, and then I'm going to make this problem easier for you to work with. Try to understand. These two objects are in contact with each other. How much is the total mass here? Total mass.
4m.
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 Remember this.
4m.
You're going to apply a force onto this object, and this F force is going to accelerate the total of this 4m mass. Because they're in contact, it is essentially obvious that X is going to push object Y, and Newton's third law tells us Y is going to also push X. True, but as they're going to move along this plane under the effect of this force F, they must have the same acceleration. Can we agree on this fact?
Yes.
Yes.
They're going to move synchronously, side by side. So they cannot have different acceleration. Now, if I assume the acceleration of both the objects is going to be A, I can pretty well write from Newton's third law that F equals to 4m into A. Can we agree on this equation? This is the Newton's third law, Newton's second law.
Yes.
Do you guys know Newton's second law?
Yes, sir.
For those of you who don't know this, Newton's second law is the basic version of Newton's second law is F equals to ma, which actually tells us that the mass of an object, the force exerted on an object is equal to the mass of the object into acceleration of the object. This is the basic formation. I wrote 4m because in this case, for my example, I used 3m and another m, so that's why I wrote the mass to be 4m. So this will be my thing. And now if I calculate the acceleration, subject acceleration out of it, the acceleration of each of the object would be F by 4m. So now have a look. This acceleration is true for X. This is also equally applicable for Y. Now if I apply this formula once again, exclusively for the two objects, how much force would the X object require to maintain this acceleration? I can write this as mass of X into acceleration of X. Can I write this equation? This is the same equation as F equals to ma, only I'm writing this equation exclusively for object X. That's why I'm using the subscript X. If I replace these values over here, have a look how much do I get. Mx is how much? 3m. What is the mass of X? 3m. And how much was the acceleration?
F
F by
by 4m.
F by 4m.
So if you do the math, how much are you left with?
3 m by 4.
3/4 of F, right?
3/4f.
Check this out. Is this calculation all right?
Sir, I did not understand this calculation.
Up till which part?
Sir, from fx into mx multiplied by ax, from that part.
This is the equation that I've written for exclusively for the object x, which is the basic equation of F equals to ma. But I try to denote this thing using the subscript x because I only wanted to calculate how much force. Listen to this part very carefully. I only wanted to calculate how much force is required by the object x to maintain an acceleration of a. Thank you. How much force is required by the object x to maintain an acceleration of this much. So that I mean, if I write a equals to this is essentially equal to, this acceleration is basically equal to acceleration of x. It is also equal to acceleration of y. Do you agree to this? Both the objects have the same acceleration.
Yes.
So that's what I replaced over here. Mass of x is 3m from the figure. Acceleration of x is this much. I replace that. M and n crosses out each other, so you get 3 by 4f. That's the calculation. বুঝে গেছে এখন?
Yes, sir.
Achha. So this means that to maintain this acceleration, object x requires 3 by 4f for its own. But how much did we apply on object's x side? How much did we apply? F. Out of this f available, f amount of force, it is using 3/4 of this part for its own acceleration. So how much is left? Do the basic math.
1/4.
F minus 3/4 of f gives you 1/4. So logic should tell us that this 1/4 of F force should be exerted on the object Y, because you are, let's say you are feeding the F object a value of, let's say, 40 Newton. I'm choosing the value 40 Newton because it's a good fraction. We can very easily divide it into 4. Let's say if F is 40 Newton, object X is gonna use 30 Newton out of it because that's the fraction 3/4. And how much should it have remaining? 10. It is
10
gonna
Newton.
exert 10 Newton force onto this object. Now let's give a calculation that can we get this number for Fy calculation. Let's say if I do the Fy calculation, Fy equals to how much? My into Ay, right? If I go ahead and replace the values, My is m, Ay is F by 4m. I'm just replacing values over here. This is replaced this one from the figure, mass of the y, and acceleration of y was replaced from this part over here. So how much do you get? M and m crosses out each other. You get 1/4 of it, right? So you can see it very well that once we have applied the F force onto the object X, whatever that value is, I use the 40 Newton as an example. It doesn't have to be 40 Newton. Object X will use 3/4 of that available force for its own acceleration, and it will provide the remaining force onto the object Y, so that object Y could also accelerate its own self. The entire logic of this whole point of this whole question was that both of the objects should have the same acceleration since they are in contact with each other. এই পর্যন্ত ক্যালকুলেশনটা বুঝা গেছে কিনা?
Yes, sir.
Yes, sir.
লজিক্যালি কনসিস্টেন্ট, ঠিক আছে? আচ্ছা, এখন আমি একটা ব্রেক নিতেছি। It's 7:06, so we'll resume class at 7:15 and 7:15 or yeah, we'll resume class at around 7:15 and we'll have another 15 minutes of class. So we are having a break for prayer, Maghrib prayer.
Okay, sir.
So the point,
Sir?
yes,
I had a question.
go ahead.
কিসে এফ ফোর্সটা হচ্ছে এক্স এর উপর দিলে তারপর এক্স হচ্ছে 3/4 যে ফোর্স ওয়াই এর উপর দেয়, রিমেইনিং ফোর্সটা কি হবে?
না, X 3/4 ফোর্স নিজের অ্যাক্সিলারেশনের জন্য ইউজ করে।
আচ্ছা।
For example, if the value of F is 40 Newton, let's say, then X will use 30 Newton of force for its own acceleration. যেটা সে নিজে ইউজ করে ফেলবে, বাকিটুকু সে y এর উপর ট্রান্সফার করবে।
আচ্ছা, বুঝছি।
Beautiful. So the point that I'm trying to make is that whenever any object is subjected to a force, if it uses a force for one purpose, it cannot do other one. What I mean from this, what I want you to take from this example is that because x is using 30 Newton force for its own acceleration, provided the f is 40 Newton, it cannot give any part of the 30 Newton force to the y. It can only give the other 10 Newton force to y. Because x used 30 Newton force of its available 40 Newton force, it could give the other 10 Newton to y. It could not give any more than 10 Newton because it had to use 30 Newton for its own acceleration. So point to be noted, if certain portion of available force is used for one purpose, it cannot be used for another purpose because x used a part of the force for its own acceleration. It could only provide the remaining force to y. Now comes the idea for weightlessness. So listen to me for this part very carefully. The first sentence that I really wanted to appreciate and remember: weight and weightless and the sensation of weight, they are not the same thing. Weight and the sensation of weight, they're not the same thing. What I'm meaning is this: the way we experience weight is how do we know that we have a weight? If we experience weight by the reaction force, the surface that we are on, that we experience. Think about this. Let's say if you're standing on ground, the lower surface of your feet, they experience an upward force which produces some compression on your skin, which you sense as weight. So you don't essentially sense the exact force by which the earth pulls you down. You sense the reaction force that you exert on a surface. If you're sitting down, then you're experiencing a force on your thighs and your hip. That reaction force is telling you that you are subject to it. You are experiencing an upward force which gets processed in your brain that because I'm experiencing an upward force, but I'm not moving anywhere, or I'm stationary. It means I'm also being pulled downwards by equal force. Two forces balance out each other. So I have weight. So we don't experience weight. We actually experience, or we actually get the sensation, or we actually sense the reaction force that we get because of weight from the other surface. First, appreciate this. Weight is because of the attraction of earth and myself, but I will not experience that force directly. I will only experience what is the reaction force that I get from other surfaces because of this downward pull. So that's how we sensation weight. So the idea of weightlessness is that if in any case, it is such a scenario that we are subjected to weight, we have weight, but we do not exert any part of that available weight onto any surface. We use that weight for something else other than applying that any part of that force on a surface, then we will not sense weight. That is what we call weightlessness. It's not weightless, it's weightlessness. It means it appears, or it feels to us as if we don't have weight, but we do have weight, but we do not sense it anymore. One of the simple example is that if you take a jump from a high enough building, let's say you have enough cushioning surface, big balloons and cushioning bags and everything. If you take a jump from a 10-story building, in that case, for the duration of your fall, you'll be using all of your available weight to accelerate yourself. If we consider resistance as a negligible force, because you'll be using up entire of your available weight to make yourself accelerate, actually speed up, you cannot exert that force onto any surface because you are actually taking a jump. That's when you will not sense weight. For that duration of your fall, you will feel weightlessness. But that is not the case if you take a jump from a 200-story building. Obviously, you should have some parachute with yourself if you do that. Whenever you take a jump from 200-story building, let's say you fall by 50-story or 100-story, by falling that much height, you are gonna get enough speed that you are gonna start experience a very strong upward acceleration. Now you are having a reaction force, not from any hard surface. You are having a reaction force from the atmosphere. As you are falling down, you are pushing down on the air molecules in a downward direction. By Newton's third law, the air molecules are also pushing you in the upward direction, which is basically the air resistance. You can sense that reaction force from those air molecules, which you can sense as your weight. But if air resistance was negligible, you would not be sensing that. What happens in space, or to be more exact, what happens in the space station where we actually see objects or persons actually have weightless, they are floating around. This is a very simple thing to explain. Let's say this is Earth. I'm gonna draw this with brown. I'm gonna fill it with brown color. Let's say this is Earth, and let's consider this is the track of a certain circle. Circle মানে হচ্ছে, let's say this is the orbital track of a satellite. What just happened? Nothing happened. Let's say this is the orbital track of a certain satellite. Let's say this is the satellite. If inside this satellite, let's say this satellite is blue, and I'm gonna fill it with blue. So if we consider, if this satellite, I mean, the way any satellite work is that they go around the Earth at a really high speed, and they maintain this circular orbit. Now, here is a catch that you have to understand. Maintaining this circular orbit means that this satellite, which is basically a, do you guys understand what a satellite is?
Yes, sir.
Moon.
Yes, sir.
Moon is the natural satellite. Everything else are artificial satellites. So a satellite is something that goes around a planet, and then planet is which goes around a star. So that's how we classify the astronomical stuffs. So the way this object can maintain an uniform track like this is if it gets a perfect balance of forces. What is that balance of forces? Think about this. If we place the satellite over here stationary, it can never remain stationary over here. It's going to essentially get attracted by the Earth, and it's going to be slowly falling towards the Earth and atmosphere, and eventually it's going to hit the Earth's surface. The only way we can make this thing go around in circle is that if we set this in a circular motion path. Let's say at this point the velocity is working in this direction at such a speed that whenever I mean, try to understand, whenever, let's say the object is at one point is over here, after a while the object comes up over here, and at this point its instantaneous velocity will also be tangent to the circle at this point, which means you're going to have a velocity like this.
Centrifugal force.
Centripetal force. I'm coming to that point. So what I'm trying to show you is that the magnitude of the velocity is same everywhere, or the speed of the satellite is same everywhere, but essentially the directions are not same. You can see over here, this was aimed in this direction, this has a bit more slanted. If the satellite comes up over here, you're going to have even a more changed direction, which means as the satellite goes around the track, it continuously experiences change of direction. And since velocity is a vector term, so delta V can happen from change of magnitude. It can also come from change of direction. In this case, that change of direction is set to such a high value that the centripetal acceleration, or the acceleration towards the center of the Earth, this is the acceleration. I should have drawn this with different color. Let's say I'm going to show the acceleration with red, let's say. So it experiences an acceleration towards the center of the Earth. Let's say this is the acceleration towards the center of the Earth. Now that's how any object undergoes circular motion, that to make this change of velocity happen, we have to have a centripetal acceleration, which is going to maintain the circular motion. What the satellite does, the way satellites are set in their orbit, that this force that they are gonna have to, that this satellite have to use to maintain the circular motion. Try to understand, to maintain the circular motion, the object has to have this force. This is pretty simple for you to understand. If I give you a physical example which can make sense to you, if you tie up a stone with a piece of rope and take it in your hand and start rotating it at a pretty high speed in circular motion, you'll find out as long as you keep rotating the spin, rotating the rope is going to be always taut. Do you understand what this word means, taut?
Yes.
Taut means not slack. It means it is tan, man ekdom soja, straight. Okay. So the rope is going to be always taut. The reason the rope always remains taut is because naturally, because of its own inertial behavior. Inertia means inertia is the tendency of objects to maintain its velocity at that instant. Maintaining its velocity means maintaining the direction, also maintaining the magnitude. So the object is essentially trying to maintain its velocity. It means object is always trying to get in this direction, or it's trying to go tangentially out of this circle, but it cannot do that because you are continuously pulling the object towards the center by the attachment of the rope. So you are always producing an inward force onto this stone, and that is what is keeping your rope taut. So the object is trying to skid outwards, but not radially outwards, tangentially outwards. Try to understand. If you keep rotating this stone pretty fast, and then if you let go, it's gonna get away from you, but it's gonna go tangent with the circle. Which means that if you have your rope, if this is the circle that you are rotating the thing, and let's say this is your stone, I'm gonna throw the stone with a random size. For example, this is the stone, and this is the rope that you're holding over here. If you let go of the stone at this position, this stone is gonna go in this way. If you let go of the rope at this position, this stone is gonna go in this direction. Not like this, not like this. This never happens. Do you understand?
Yes, sir.
Yes, sir.
Okay. So this never
Is
happens.
it always mandatory that it will occur in a tangent way?
Yes, because the velocity is tangent. The object's instantaneous velocity is tangent. I mean, if you are a very small person, let's say Ant-Man squeezed down, and if you're sitting on this stone and looking at any instant, I mean, when the stone is over here, your viewpoint is going to be in this direction. If you're sitting over here, your viewpoint is going to be in this direction. As the stone continuously rotates, if you're in the driving seat of the stone, you're going to be always having your direction changed. So the stone is trying to get out of the circle, being tangent with the circle, and because we are continuously pulling by the rope, we are keeping the stone in that circular track. The point that I'm trying to make you understand is that to maintain the stone within this circular track, we have to continuously pull the rope inward. Because of that inward force, the stone will undergo the acceleration or centripetal acceleration, which is going to cause it to go around in circles. Similarly, that exact thing happens for the satellite as well, but only in this case, the satellite does not have a rope attached to the Earth. It has the gravitational force, which is weight. So what is happening? The Earth is continuously pulling the satellite towards the center along these red lines. But we set the satellite at such a high speed that it is going to always use all of these force. This is the important point, all. Important word. We have set the satellite at this orbit at such a high speed that it is going to use all of its available weight to maintain the circular motion. Which means circular motion maintain করার জন্য আমাদের যতটুকু force লাগবে weight থেকে ওই পুরো force হবে. So if the weight of this object over here is, let's say 1000 Newton, it is going to use entire 1000 Newton to maintain circular motion. This satellite is going to maintain circular motion by using this entire 1000 Newton force, which means this weight will be used up for circular motion. Since the weight is already being used up for circular motion, and this is equally applicable for the satellite and all the stuff that is inside the satellite as well. So a satellite ভিতরে যদি একটা মানুষ থাকে, let's say if I zoom in and try to draw a human over here, inside here, I'm not sure if I can do that properly, but I can try. Let's say if we do have a human over here, as the satellite is moving around at a pretty high speed, this human is also moving around at a pretty high speed as well, because he's inside the satellite. So he is also using his own weight to maintain the circular motion. Because his weight is being used up to maintain the circular motion, which is a centripetal force, he cannot exert that weight onto the surface of the satellite. So as the satellite goes around the Earth, using all of its weight as centripetal force, the person inside the satellite also go around the Earth using all of his weight as centripetal force for his own self. Now, because the person is using up all of their weight, they cannot exert any force onto any of the surfaces. This essentially makes the person to experience weightlessness. His weight is not essentially zero, but because he's spending all of his available weight force to maintain the circular motion, he cannot exert any of the available weight force onto any surface and sense weight. Like I said at the very beginning, that weight and sensing weight are not the same thing. The way we understand we have weight is not that we experience the attraction of the earth, rather we experience the reaction force of a hard surface or the atmosphere in the opposite direction of the earth's pull, and that's how we sense as weight. Now, because this person who is located inside the satellite is going to use up all of his available weight to maintain circular motion, he cannot exert any force onto onto any inner surface of the satellite. So basically, he can move around or float pretty easily. Because why is that? Because he's spending all of his available weight to maintain the circular motion. So because the forces got spent in one purpose, which is circular motion, any part of the available weight cannot be used to push onto any surface. So because the push is not there, there is no reaction force, the person does not sense weight. That does not mean that the person does not have weight. The person does have weight, but that weight is not being exerted onto any surface. That weight is
Does
being
the moon do the same thing?
exactly same thing. Moon also does the same thing, but because moon is a pretty massive object, if we are located on the surface of the moon, we would be also attracted on the moon. For example, if this figure is definitely not drawn to scale.
The tides.
Yeah, exactly. So if we are located on the surface of the moon, let's say if this was the moon, if we are located on the surface of the moon would also pull us downwards by a pretty strong force. That force is not going to be as strong as the pull of the earth. The moon's gravitational acceleration is about 1/6 of that of earth. So moon is going to also pull us down towards its own center, but that would be the weight experienced because of the moon. Whenever we are on moon, we are not going to experience the force by which the earth is pulling us towards itself. That force we cannot exert on moon. We can only exert on the moon the force by which the moon pulls us towards itself. That's why whenever we reach to moon, we do not experience the earth's gravitational field anymore. But if you wonder, does the earth's does the attraction on the earth, attraction of the earth on the person stops working? The answer is a solid no. The person,
No.
that force still works, but that force is being used up to go around the earth at a pretty high speed as the moon is going around the earth.
I was saying about the moon. Does it do the same thing while it rotates around the earth?
Yes. It uses all of its weight to go around the earth. The answer to your question is yes. So could I give you a better understanding for what is weight and what is weightlessness and what actually happens in the space? Does this idea make sense?
Yes, sir.
Yes, sir.
আচ্ছা যারা orally response করতেছে না একটু chat window থেকে সেটা লেখো yes or no.
Yes, sir.
Yes, sir.
We'll call it a day. I'll just call it a day right now, but I need you to I need to make sure that you got this point.
Yes, sir, we got it.
Yes, sir.
Yes, sir.
Appreciate this. So it's past 7:30. Although we started quite late, but I have another class to catch up with. So for today's class, we'll call it a day. I actually still did not answer Arif's question. Arif, you what is the question that you actually asked me? I actually forgot.
I asked about the feather, that about what does it have any downward or upward like this velocity. I asked to you about this, about the feather.
Acha, yeah, the feather question. Yeah, I'll definitely start my lecture with that question in my mind in my next lecture. Just remind me at the beginning of the class. Okay.
Okay.
That will be the continuation of this lecture further on. Kids, thank you very much for the additional 5 minutes of attention. I love you all, and we'll call it a day for today. Thank you very much.
Assalamu alaikum, sir.
Thank you, sir.
Assalamu alaikum, sir.
দেখা হবে স্যার।
Assalamu alaikum, sir.
দেখা হবে।